Hello everyone. In the last session, we talked about that what exactly a relation is, what is Cartesian product, how we can define the relation, and the terminology is explained by taking the various examples. We also discussed few of the real-world application of the relation. Now, in the today's session, we are going to discuss the different types of relations that we are having. The different types of relation that we are having. There are a variety of the relations that are used to program some automated system, we can say, to program some chatbots, as these are one of the applications. Okay, so let us try to understand that what are the different types of relations we are having. The first one is called as the identity relation. Let me define it as, suppose that we are having a non-empty set A. Let us consider a non-empty set A and having it is having some of the elements. Let us take it as 1, 2, 3. A is having some element 1, 2, 3, and I'm defining a relation R from a set A to A itself. Okay, do remember it. We are talking about these types of relation on a set A to itself. On a set A to itself, this relation R we call as a identity relation if we call it as identity relation if A comma A if A comma A belongs to your R. If A comma A belongs to your R, where what is A? A belongs to your set A. If A comma A belongs to your R, where A is belongs to A only. Or let me just write it in the more descriptive manner. A relation R is called as a identity relation. A relation R is called as a identity relation if every element is related to itself only. A relation is called identity relation if every element is related to itself only. Here, this word only is having one of the most important significance. We'll take the example on it after the second definition. The second is reflexive relation. A relation is called as a reflexive relation if it is having A comma A belongs to R for every A belongs to A. For every A belongs to A. For every A belongs to A. Where A for every means for every choice of A from the set, for every is there in both the definition. We call the relation as reflexive. If A comma A is in R, for every A belongs to your set, a relation is called identity relation if A comma A belongs to R only. Now, what is the difference between the two? The first definition is saying that A must be related to itself only for every choice from A. On the second side, reflexive is saying A must be related to itself. There is no restriction that this A will be paired with the other elements or not. But this is mandatory that it must be paired with itself only, itself too. Suppose R is having element as, I am taking R as an element, let it be 1 comma 1. Can I call this relation as a reflexive relation? R is having one element which is 1 comma 1. Can I call it as reflexive? The answer is no, it is not reflexive. Why it is not reflexive? Because it is there that A comma is there in your R for every choice of A. If I am taking 1 comma 1 is there, yes. 2 comma 2 is not there, so not reflexive. Okay, do remember one more thing about these spatial relation. We will call it as yes if every possibility satisfying the rule. Every possibility. We will say no if we are able to find at least one counter example, one situation which not satisfying the condition. Like over here, I can say like 2 comma 2 does not belongs to your R, so the relation is not reflexive. The relation is not reflexive. On the same side, can I say it is identity? So the answer is no. For identity also, it is said that for every A must be related to itself only. So 2 comma 2 is not there, 3 comma 3 is not there. So this relation is not reflexive as well as not identity. Let us take one more R. This time I am taking some elements in R, or let us update this relation only. So if I'm updating this relation and adding few more element in it, let us add few more element in it. This time R is having element 1, 1, 2, 2, and 3, 3. Can I say this relation is identity? The answer is yes. Every element is related to itself only. 1 is related to 1 only. 2 is related to 2 only. 3 is related to 3 only. So yes, we will say this relation is an identity relation. Every element related to itself only. Can I say it is reflexive relation? So the answer is yes. For every choice of A is related to A. If I take 1 from set A, 1, 1 is there. If I take 2 from set A, 2, 2 is there. If I take 3 from set A, 3, 3 is also there. So for every choice of A comma A is there. So this relation is both reflexive as well as identity. If I'm writing one more relation, let us see it is having element 1, 1, 2, 2, 3, 3, 2, 3. This time R is having these four elements 1, 1, 2, 2, 3, 3, and 2, comma 3. Can I call this relation identity? The answer is no. Why no? Because just see this only statement. It is saying whatever A you are taking from your set A, it must be related to itself only. Like if I take 1, 1 should be there with 1. Yes, satisfied. 2, 2 should be there by 2. But 2 is also there with 3. 2 is also there with 3. So what should I say? 2 comma 3 is also there in your R. So the relation is not identity relation. Now I hope you get clarity that what this meaning of only is. A single individual is connected to single individual only, which is itself. It should not be connected by some other. So this is how we define the identity relation. Can I say this relation is reflexive? The answer is yes. We can call this relation as reflexive. Why? Over here it is said that A comma A is in your R for every choice of A. If I take 1, 1, 1 is there. If I take 2, 2, 2 is there. If I take 3, 3, 3 is there. So for every A comma A is there. Reflexive relation doesn't tell anything about other ordered pair. That either A should be related to some other B, C, or D or not. If it is yes, no problem. If it is no, no problem. The only thing is what the relation reflexive said that every element must be related to itself only. So yes, this relation is reflexive relation. Understood? So for identity, only A comma A should be there. For reflexive, A comma A must be there. For reflexive, A comma A must be there. No restriction on the other choices. A comma A must be there. No restriction on the other choices. Other choices may be there, may not be there. No problem with it. So now, can we generate some relation between these two relations? Yes, we can say every identity relation is reflexive. Every identity relation is reflexive. But every reflexive relation need not be identity. Like over here, you can see this R. This R is reflexive, but not identity. This R is identity, but also reflexive. Identity relation is always unique. Only one identity relation is generated for a set A. All A comma A, do list all A comma A, this is your identity. But we can write many of reflexive relation. For example, this is your reflexive, this is your reflexive. I can write one more reflexive relation on the same set 1, 1, 2, 2, 3, 3, then I will take 2, 3, I will take 3, 1. This is also a reflexive. And you can see both of the relation are different. The first one having 4 elements, the second, this is having 5 elements. So they are not equal relation, okay? Two different. So I defined 3 identity relation on this set A. I can define many more. I can define many more reflexive relation on this set A. But identity relation is only one, which is 1, 1, 2, 2, 3, 3. This is the only relation which is identity on this set A. Okay, I hope you understand the difference between the two. The third one, we are having anti-reflexive or irreflexive relation. A relation is called as anti-reflexive or irreflexive if first thing we should be very much clear that it is not opposite of a reflexive relation. A relation can be simultaneously not reflexive or not irreflexive. We'll take the example also. Anti-reflexive or irreflexive, what it says that A comma A does not belongs to R for every choice of A from set A. For every choice of A from set A. A relation is called irreflexive. A relation is called irreflexive or anti-reflexive if A comma is not there in your R for every. So in simple word, we can say none of A comma A should be there. Not even a single A comma A is allowed. Not even a single A comma A is allowed. If I take one relation which is let it be having element 1 comma 1 and 2 comma 2, can I say this relation is anti-reflexive? The answer is no, because it is having 1 comma 1. And as per definition, none of A comma A is allowed. As per the definition, none of A comma A is allowed, but it have 1 comma 1. So we'll say this relation is not anti-reflexive or not irreflexive. Can I say this relation is reflexive? Can I say this relation is this is not anti-reflexive first? Can I say this relation is reflexive? The answer is no. It is not reflexive. Why not reflexive? 3 comma 3 does not belongs to R. So we can't say if a relation is not anti-reflexive, it will be reflexive. If a relation is not reflexive, it will be anti-reflexive. We can't say. Okay? So be careful in this definition. A relation is called as an anti-reflexive if none of A comma A is there. One more example I will take R having element 1 comma 3 and 3 comma 1. I take one more relation R which is having 1 3 and 3 1. Is this relation is anti-reflexive? The answer is yes. It do not have any A comma A. It do not have 1 comma 1. It do not have 2 comma 2. It do not have 3 comma 3. We are defining relation on this 1 2 3. So yes, we call this as an anti-reflexive relation or irreflexive relation. Is it reflexive? The answer is no. Is it identity? The answer is no. Okay, so this is how we define anti-reflexive. None of A comma A is allowed. Even a single A comma A is there in your R. The relation is not irreflexive. The relation is not irreflexive. Moving to the third category, we call it as symmetric relation. So a relation is called symmetric. Now onwards, we are having the conditional relation. What we mean by conditional relation? Let us try to understand. A relation is called symmetric relation if whenever A comma B belongs to R, then B comma A must be in your R. Whenever A comma B belongs to R, whenever A comma B belongs to your R, then B comma A must be there in your R. Where A and B comes from your set A. A and B comes from set A. So if this condition satisfies, we call the relation as symmetric relation. What it means if in your R 1 comma 2 is there, then 2 comma 1 should also be there. If 3 comma 2 is there, 2 comma 3 is also there. Okay, input output change. Both the pairs should present in your relation. Such relation we called as a symmetric relation. Such relation we called as a symmetric relation. Let us take few example on it, on symmetric relation. So let me rub it something over here. And then I will take the example. A comma B is there, B comma A is there, then relation is symmetric. And it is a conditional relation. That means what? If A comma B is there, then B comma A must be there in order to make the relation as symmetric. In order to make a relation as symmetric. For example, let us take a relation R having element 1 comma 1, 2 comma 3. Is this relation is symmetric? Let us take by pair. 1 1 is there, 1 1 is there, no problem with it. 2 3 is there, but 3 2 is not there. Not symmetric. How to write it? We can say 2 3 belongs to R, but 3 comma 2 does not belongs to R. So this relation is not symmetric relation. Quite simple. If A comma B is there in your R, then B comma A must be in your R. Otherwise, the relation is not symmetric. If I take one more pair, let us take this time. I am taking it as 3 comma 2, then like this, like this. So is it symmetric? The answer is yes. 2 3 is there, 3 2 is there. This pair satisfies the condition. 3 comma 3, 3 comma 3. Both the direction here is it satisfying the condition. If I take yes, so this relation is symmetric. Understood? Conditional statement means what? It is a kind of conditional truth table, conditional logic. And what conditional logic truth table said? It says that if condition satisfy, then we are supposed to check then condition. If condition satisfy, then we are supposed to check then condition. And if then condition not satisfy, not symmetric. If then condition satisfy, symmetric. The second case, if your if condition not satisfy, then we are not supposed to check then condition and we will say yes for that relation. Okay, be careful with this statement. If your condition not satisfy, we are not supposed to check then condition. Like suppose that if 2 3 is not there, why should I check 3 2? If 1 3 is not there, why should I check 3 1? Understood? So if condition is not satisfied for any pair in your R, we call the relation is symmetric. So two condition in order to a relation is symmetric. One, if condition not satisfy. Two, if condition satisfy and then condition satisfy. So these are the two scenario where a relation is symmetric. Where a relation is symmetric. The scenario for no, if condition satisfy, then condition not satisfy. So only one scenario when relation is not symmetric is what? When your if condition satisfy, but then condition not satisfy. If condition satisfy, but then condition not satisfy, for this case, we call the relation is not symmetric. Otherwise, it will be always symmetric. Okay, so this is how we can define a symmetric relation. The next relation that we are having is anti-symmetric relation. Anti-symmetric relation is what? A relation is called, it is also a conditional relation. What it says, if A comma B belongs to R, B comma A belongs to R, then A must equal to B. Very important condition. A relation is called anti-symmetric relation. If AB is in your R, BA is in your R. This is what we call as a condition. So this is the condition. If this condition satisfies, then we must say that A and B are equal elements. If this is true, the relation is anti-symmetric, otherwise not anti-symmetric. For example, if I am talking about the relation first, if I am talking about this relation 1, 1 and 2, 3, 1, 1 and 2, comma 3, can I say this relation is anti-symmetric? Can I say this relation is anti-symmetric? Let us try to check it for every pair. If I am taking pair as the first element, so first element, so I will say 1 comma 1 belongs to R. Yes. Reverse it, which will give you same thing. 1 1 is belongs to R. Yes. 1 equal to 1. Yes. So first pair satisfying the condition. Remember, when every pair, every individual satisfying the condition, then only we will say yes for a relation. If there is a single pair which do not satisfy the condition, we'll say no for that relation. General result. Okay. Whatever relation you are checking, for yes, every time yes. For no, a single time no is needed. Okay. So, for example, like when we are saying someone is good, he or she must be good with you every time. If he or she did anything wrong with you, you will say no, he is not good. So, kind of this situation we can relate. No means a single incident when the relation is not satisfied. Yes means every time it must satisfy. So, for pair, this it is satisfy, yes. If I take the second pair, so 2 comma 3 belongs to R. Can I make the second condition B comma A? What about 3 comma 2? Does not belongs to R. So this pair is not making if condition. So we are not supposed to check whether 2 is equal to 3 or not. Be careful once again. When your if condition not satisfy, when your if condition not satisfy, we are not supposed to check then condition. Okay? Since it is a conditional statement, as already told you, in conditional statement, if condition satisfy, then only we are supposed to check the outcome or then condition. If condition not satisfy, we will say yes for that relation for that particular pair. So over here, the condition not satisfy, so we will say yes for this pair also. So there are two pairs, both of them satisfying the condition. So we'll say the relation R is anti-symmetric. Understood? If condition satisfy, then only then condition need to be checked. If condition not satisfy, no need to check for then condition. We will say yes for that relation. We'll say yes for that relation. A conditional statement. That's how inputs in a computer system work when we deal with logics. Okay? Anti-symmetric relation. Now taking one more relation, let us take one more example. This time I am having 1 comma 2 and let us see one more example 2 comma 3. Can I say this relation is anti-symmetric? Let us check. One first pair, 1 comma 2 is there, but 2 comma 1 is not there. For anti-symmetric, condition is what AB and BA both must be there. So 1 2 is there, but 2 1 is not there. So this pair not satisfying the condition. So I will not check it whether 1 equal to 2 or not. The second pair, if I make 2 3 is there, but 3 2 is not there. 2 3 is there, but 3 2 is not there. So once again, this pair not satisfying the condition. So should I check 2 equal to 3 or not? No, it's not needed. So in both the pair, the condition is not formulated. That's why we are not supposed to check then condition. And what happens if every pair or if pair does not satisfying the if condition, will say yes for that relation. So this relation R is anti-symmetric relation. This relation R will anti-symmetric relation. The answer is yes. Is this relation is symmetric? The answer is no. Why it is not symmetric? Because in symmetric, if condition is AB in R, and then condition is BA in R. So 1, 2 is there, but 2, 1 is not there. So I find one pair, 1, 2, which is there in your R, but on the same side, the then condition 2, 1 is not there in your R. So this relation is not symmetric. But yes, this relation is anti-symmetric. Moving next relation, asymmetric relation. It is also a conditional relation. What it says that if A comma B belongs to R, then B comma A does not belongs to R. A relation is said to asymmetric if AB is there in your R and BA is not there in your R. This is your condition. This is the condition, and this is what the outcome or the conclusion that we are supposed to check. If then, can I say this relation is asymmetric? 1, 2 is there? Yes, but 2, 1 is not there. This pair satisfying the condition. 2, 3 is there, 3, 2 is not there. Satisfying the condition. So both the pairs satisfying if and then condition. So we'll call this relation as asymmetric relation. We'll call this relation as asymmetric relation. Asymmetric relation. On the same side, if I'm talking the previous example, which is this one, can I say this relation is asymmetric? The answer is no. Why no? 2, comma 3 satisfying the condition. Yes, 2, 3 is there, 3, 2 is not there. But what about 1, 1? So 1, 1 means what? We are saying 1, 1 belongs to R, and then 1, 1 should not belongs to R. Can it prove parallelly? No. If 1, 1 is there, then 1, 1 is there. So this pair satisfying if condition, 1, 1 is there, but not satisfying then condition. So this relation is not asymmetric relation. So this relation is not asymmetric relation. Asymmetric means in asymmetric, AA is not allowed. AA never allowed. On the same side, if B is there, then BA is also not allowed. Then BA is also not allowed. Such relation we called as a asymmetric relation. Moving next, the next relation is transitive relation. So what a transitive relation? It is also a conditional relation. It says that if A comma B belongs to R and B comma C belongs to R, then A comma C must belongs to R, also called as a chain rule. Means this is your if condition. This is your if condition, or we can say the conditional statement, and this is your then condition. If your if condition satisfy, then we are supposed to check then condition. Then we are supposed to check then condition. If condition not satisfy, then condition is not needed to be checked, and in this scenario, the relation is yes. The transitive will say yes for that particular relation. There is no restriction on ABC over here. These ABC may be anything from the given set. They may be all three are equal, two of them are equal, all three are different. Okay, many times we like assume in our mind ABC means they should be different. No. So it's not. They may be same, they may be different, some of them same, some of them not same. Now let us check this relation is transitive or not. So we can say A comma B belongs to R. Yes, 1 comma T is there in R. B comma C is also there. So 2 comma 3 is also there in your R if condition satisfy. Do remember the connecting element must be same. This connecting element must be same. 1, 2, 2, 3. Okay, A, B, B, C. Whatever choice you are taking, the connecting or bridging element must be same. So 1, 2 is there, 2, 3 is there, 1, 2 is there, 2, 3 is there. So as per this condition, what should be the A comma C? So first to last. As per this condition, 1 comma 3. 1 comma 3 should also there in your R, but it is not there in your R. 1, 3 is not there in this R, so this relation is not transitive. This relation is satisfying the condition if condition satisfy. 1, 2 is there, 2, 3 is there, and means 1, 3 should also one there. So we can understand it like we are having somewhere A, somewhere B, somewhere C. Moving from A to B, moving from B to C. Then we must move from A to C. We must move from A to C. This B is called as a connecting element or bridging element. Connecting element or bridging element. So when we are taking if condition, we must be very much careful that this bridging element must be there. Otherwise, this if condition will not work. Make choose those pair which satisfying the condition in a manner like AB and BC is there. Now taking one more relation, like suppose that this time I am having R having 1, 1, 2, 2, and let us take it as 3, 2. So can I call this relation as transitive? Let us try to make pair. If I'm making pair with 1, 1, so 1, 1 means what? A, B, C, all three I am taking 1. So A to B is there, B to C is there, A to C is also there. Like 1, 1 is there, 1, 1 is there, so 1, 1 is there. So this pair is satisfying the transitivity condition. Yes. Let us take the second pair. Can I take the pair in this manner 2, 2 and 3, 2? I am taking the pair in this manner 2, 2 belongs to R and 3, 2 belongs to R. Can I do this? No. The bridge element is not same in this pair. So this pair can't be taken. This pair can't be taken, and on this basis, I can't say anything. So let us take the pair in some other manner. Do remember the pair can be taken in any direction. So now I am taking the pair as 3, comma 2. Yes, it is there in your R. 2, comma 2. Yes, it is there in your R. The bridging element is same. The bridging element is same. 3, 2 is in R. 2, 3 is in R. So as per this result, A, comma C. So 3, 2 should also be there. 3, 2 should also be there. And you can see, yes, it is there. So now this pair also satisfying if then condition. First is also satisfying this condition. So this relation we call as a transitive relation. So this relation we call as a transitive relation. Okay, so these are few of the relation that we are having over here. Some important relation. Try to go through with the concept. We'll take more example in the next session. Like we are having few more type of relation, which is the combinations of these. So like partially ordered relation is one of them. Equivalence relation is one of them. So these two relation is the combinations. These two relation is not the single one. They are combination. For example, if I'm talking about partially ordered relation, so a relation is called partially ordered if it is reflexive, if it is reflexive, if it is transitive, if it is transitive, if it is symmetric. No. Reflexive, transitive, and anti-symmetric. Okay, anti-symmetric. So if a relation satisfying these conditions, which is reflexive, anti-symmetric, transitive, that relation we call as a partially ordered relation. On the same side, equivalence is also satisfying three conditions. One, it must be reflexive. One must be symmetric. One must be transitive. So if these three conditions satisfy, we call it as a equivalence relation. Okay, so in the next session, we'll talk about in more detail about partially ordered relation and equivalence relation with some examples on it. Okay, so that's all for the types of relation. I hope you understand it. Now let us close this session.